首先我再次感谢国内的很多朋友同事和我一起这个work on this topic. So last time we discussed the symmetry energy and soldering correlation in nuclei and nuclear matter and how they are related to some of the fundamental questions regarding symmetry energy. But today we are going to focus on symmetry energy and the properties of hyphen nuclei and their collisions. Okay, well, you probably have seen that the topic is very big because the symmetry energy, appears almost everywhere in properties of nuclei. Of course, we want to find places where it has an important role. So this topic is quite broad. So what I would like to do is to select a few topics here. I would like to focus on the following three topics. I think they are important at this time, at least, for further constraining the symmetry energy. So I will start by discussing the incompressibility, screwness, and the kurtosis of symmetric nuclear matter. Then we'll move on to discuss the neutron-proton effective masses splitting in neutron-rich matter. Then I will discuss neutron skins of hyphen nuclei. I will spend approximately 15 to 20 minutes on each one of the three topics. But before we go on, I would like to emphasize that symmetry energy affects many properties of nuclei and nuclear reactions far beyond what we are going to talk about, discuss today. And there are many interesting papers by many people in the literature. In particular, many people in China have made important contributions in this area of research. I would also like to let you know that my opinions on these selected issues might be biased, incomplete, and may simply be wrong. So please correct me and let me know your comments. Okay, I said the symmetry energy is important for many properties of nuclei and nuclear reactions because the symmetry energy is an important term in the energy density function. Okay, when you study property of nuclei, nuclear matter, or nuclear reactions, you have to use the energy density function when you have asymmetry matter. So this is symmetry energy term will appear in many places. Last time we have discussed that the symmetry energy is basically the energy difference between pure neutron matter and symmetric matter. So the symmetry energy is a measure of the energy cost to make your system more and more neutron rich. As you go above the bottom line here is for symmetric nuclear matter. Okay, now many of you in the audience may have been working on some of these issues. So you may be working on fundamental microscopic theories to predict the equatorial state, and you would like to know what's the fundamental underlying physics behind each term in your equatorial state. Similarly, in experiments, people are trying to study the physics behind each observable, and of course we like to make connections between these two areas. Sometimes you can do direct comparisons. Sometimes we may want to characterize the different terms of your equatorial state by using some coefficients, by expanding the symmetric part of the equatorial state and the symmetry energy as a function of densities. So you are going, many of you are familiar with this terminology. It's like the K note is the incompressibility of symmetric matter. Z note is the screwness of symmetric matter, or Z note is the kurtosis, is the coefficient of the fourth power of density. Similarly, for symmetry energy, when we expand it in terms of density, we have the slope of symmetry energy, the curvature of the symmetry energy, screwness of the symmetry energy. Okay, so we're going to spend time discussing in particular coefficient of symmetry energy. But the reason I would like to spend some time to discuss the coefficient of symmetric matter is because the two parts of the equatorial state are strongly correlated when you study some of the experimental observables. Essentially, there's no way to determine, for instance, exactly the incompressibility of symmetric matter without knowing some of the coefficient of the symmetry energy. Okay, so that's one of the point I would like to discuss during the next few minutes. Based on many studies over the last 40 years or so, we do have some information about the limits, the range of these different parameters. For instance, the K-note, the incompressibility, has been known to be around 240 plus minus 20 MeV. And we discussed last time the magnitude of symmetry energy, the slope of symmetry energy has been constrained to be around these values. But the high order coefficients of the expansion here, both symmetric matter and asymmetric matter, are poorly known. So I mentioned that the K infinity or K naught, okay, that's the incompressibility of symmetric matter, has been studied by looking at by analyzing the general resonance of heavy nuclei. But people have found out that the incompressibility people extracted from studying the energy of general resonance is correlated to the coefficient of this idle spin asymmetry term. Namely, this K infinity or K naught is strongly correlated with this K naught because most of the nuclei you are studying have a finite value of dart. They are all asymmetric. Okay. For instance, if you look at the energy of the monopole resonance in light 208 as a function of this K tau term, which is related to the curvature of the symmetry energy, slope of the symmetry energy, and the skewness of the symmetric matter. Okay, you see that the data, experimental data, is within this range. Okay, but you see that this energy is depends on both K naught and this K tau term. So this K tau is correlated with K naught. In order to further constrain the value of K naught here, you need to know more precisely the value of this K tau term. Okay. Also, there is an important point that by studying properties of finite nuclei, in particular the incompressibility along the equilibrium density of finite nuclei, okay, one can provide some information, for instance, about this K sim or L. Because when you look at the saturation density of asymmetric nuclear matter from symmetric matter all the way to pure neutron matter, okay, there is a saturation line along which the energy will be at the minimum for a given idle spin asymmetry. So you see that the saturation density depends on this L parameter and goes like dart square. This coefficient here is exactly the same as the saturation density of finite nuclei as a function of this idle spin asymmetry square. This I is the same as this dart. So you see this term for asymmetric nuclear matter is the same as for finite nuclei. Okay. Also, when you look at the incompressibility of asymmetric matter along the saturation line, it goes like K naught plus this coefficient times dart squared. This coefficient, okay, has exactly the same form like the K tau term for finite nuclei. So we can learn about this high order term of the equatorial state for the high order term for the symmetry energy by studying how the incompressibility of finite nuclei will change as a function of asymmetry. However, this indicates that we have to study the K infinity and K tau simultaneously because they are correlated. The progress on one of them can help us to determine the other one. Well, the nuclear physics community has spent almost like 40 years since 1980 to infer the K infinity or K naught incompressibility by studying general resonance. People have reached some kind of consensus, namely what they want to do is developing microscopic models. You use your microscopic models to study all observables of finite nuclei. And you want to first reproduce experimental observables for this finite nuclei, then use the same model to predict the incompressibility of infinite nuclear matter. Okay, that's an idealized approach. That's what the community want to do. However, up to now, there's no such model. For instance, two of the very popular models for studying the incompressibility of finite nuclei, like the relativity mean field model coupled with RPA. Okay, for instance, from Descartes. This model can well reproduce the data for light-208, but it cannot reproduce the data for tin isotope. Similarly, from the Scrum-Hardy-Fock coupled with RPA, you also predict the energy of general resonance higher than the experimental data. So up to now, okay, although theoretically, ideally, would like to have such kind of consensus model, but none of this model can do it. Okay, that's probably one of the reasons that the incompressibility of symmetric nuclear matter has been within this range for the last 40 years. Okay, so what do we need to do? Well, someone need to do something, completely different or try to do things different to break this status quo so that we can make progress. Okay, and I do know some people have been trying such things. And here I would like to give you a couple of examples my collaborator and I have been trying to do. Okay, for instance, we listed here the K naught, the incompressibility, skewness, and kurtosis of symmetric nuclear matter. Their average value based on the current literature for K naught are around 235 MeV, the Z naught around minus 200 MeV, but the uncertainty of Z naught is very big. This 1 sigma here is 200 MeV. For Z naught, the kurtosis, its average value is around minus 146, but the error bar is 1,700 something. So if you look at it, the range for this 3 sigma range from minimum value to maximum, for Z naught is between minus 5,000 to positive 5,000. So the high density part of the symmetric equatorial state is very poorly known. Okay? Based on the equatorial state of symmetric matter, you can go ahead to calculate the corresponding pressure in symmetric matter. They are related to these 3 parameters like this. Well, some of you know very well the relativistic, the high-ion community by studying high-ion reactions, like analyzing collective flow or chain production from GISI energies all the way to the AGS energies, have extracted a band, a constraint range on the pressure of symmetric matter at a function of density up to about the 4.5 times normal density, under the assumption that there's no phase transition, even at this high density. That's the assumption people made. Okay, if you are interested, some of you, I'm sure have read this science article from many years ago. So this is the pressure band for symmetric nuclear matter. Now, what we can do is to use this uncertainty band for the pressure for symmetric matter to calibrate these coefficients, these 3 coefficients, using the information we know from the current available experiments. For instance, we know K naught better than J naught and better than this skewness and better than kurtosis. So based on the information we have on K naught, for instance, can we shrink the uncertainty of this J naught? Okay. Well, here is an attempt Wenjie Xie and I tried by using the Bayesian analysis. In the Bayesian analysis, you start from some kind of prior distribution for your model parameters. You have these 3 parameters. You can assume those 3 parameters have Gaussian distributions around their average values with their own uncertainty range. And then you calculate, with this parameter set, what's the probability, likelihood for this parameter set to reproduce the experimental data. That's your likelihood function. And you do this in the Markov chain Monte Carlo process. You generate many events, steps. At the end, you analyze the likelihood over many steps to get the posterior probability distribution function for the model parameters. So here we have the PDF for K-note. Okay, you start from a Gaussian distribution at your prior. The posterior one is here. So you see that the prior PDF is based on the information from studying incompressibility of nuclear matter using giant resonance. But the high ion reaction data from the collective flow prefer a value that's significantly less than what we knew from studying giant resonance. Now the peak is at around 192 MeV. This shifting is consistent with what the people have found already at the GIS by studying chain production and collective flow by several people at GSI and also at Huzhou, Wang Yongjia, Li Qingfeng, and their collaborators there and at GSI. They have already pointed out that the collective flow and chain production data at the GSI favors a value of K-note significantly smaller than the incompressibility extracted from studying giant resonance. So here is one place where we need to do some work to understand, why, it is so. How can we better constrain the K-note value? Now, I mentioned that one of our purposes, we assume that K-note is well-known. We want to use that information to constrain the skewness and the kurtosis. You see, indeed, you start from this prior distribution. Your final posterior one is much narrower than your prior one, and similarly for J-note. So indeed, the information from collective flow help us to constrain these two higher order coefficients in expanding the equation state of symmetric nuclear matter. However, there is a caveat here. Namely, I said we now roughly from starting giant resonance, the K-note is somewhere between 220 MeV to 260 MeV. In the past, nobody has given a statistical analysis. They just say, well, K-note is around 240 MeV. It could be a uniform distribution or has a peak around 235 MeV. Now, this result here is by assuming your prior distribution of K-note is a Gaussian distribution around 235. But if you use inside a uniform distribution between 220 to 260 MeV, you see that the posterior one now peaks at the lower boundary of 220 MeV. What it says is that the flow data or chain production data, of course, prefer a lower value of K-note, and also both the flow data and the giant resonance data do not constrain, wire the incompressibility. There is also, obvious kind of disagreement. Okay, and this uncertainty affects what you can say about the PDF of the value of the high order parameter, this J-note and this one. Okay, so we need to do more work on this. So this one, attempt to better understand constraining the K-note. Another attempt we did recently is, we were kind of stimulated by the fact that people have now measured the incompressibility of finite nuclei for several sets of isotopes. Okay, so for instance, tin from 112 to 124, they have measured the incompressibility of this finite nuclei. This expansion have totally four parameters. You have the coefficient, the term related to the surface term, you have a coolant term, but these two terms are relatively well determined from calculations. Okay, they are uncertainty less than 10%. This K tau and K infinity are the ones poorly known. So with this data from a sequence of isotopes, you can just use those numbers into this equation, you can use, you can have two sides of equations to solve for two unknowns, and look at how this k infinity and k tau change as the difference between idle spin asymmetries of two nuclei you use in extracting the two unknowns, k infinity and k tau. So basically, you have two unknowns. You just need two inputs. Okay. The fact is that if you look at this one, you can solve analytically. The uncertainty of k tau and k infinity will decrease as you increase the separation between idle spin asymmetries of the two nuclei you use. So for instance, if you look at it for heavy nuclei, for which this formula is expected to work well, but for light nuclei, they are not working so well because the liquid doped kind of model doesn't work for light nuclei. But for heavy nuclei, they work well. And you see that as you go to more and more neutron-rich nuclei, this k infinity stays at a constant and will have very little error bar here. Similarly, for k tau, the error bar becomes very small as you go to more and more neutron-rich nuclei. Okay, so this may be another way of extracting these two parameters. Okay, furthermore, another interesting attempt was done by Xijun, Zhang Den, and myself using Bayesian analysis, using the available data from RCMP and Texas A&M for LIDAR 208, also information about neutron skin from PRX2. Okay, this is the posterior probability distribution function of the incompressibility K naught. You see that for TIM 120, it peaks at a lower value. For LIDAR 208 from RCMP, it peaks around 210 or so. But the result from analyzing the data from Texas A&M, it peaks at a relatively larger value. This one also, the data from Texas A&M also has a larger error bar. Well, in Texas, as many of you know, everything is big. Okay, even the uncertainty of this data is also big. So take my talk today with a grain of salt. Otherwise, you take your own risk. Okay, but anyhow, if you combine the data from Texas A&M and RCMP and look at what is the best value you can extract for K naught, it's around this number here. So this 223 MeV is about the lower value of the fiducial value for K naught. Okay, the lower limit of this fiducial value of 220 MeV. This number has been there since 1980. So indeed, we can reduce the uncertainty range a little bit. But looking at this picture here, you see that the data itself needs more verification, make them more consistent. Okay, so these are some of the recent attempts. You see that the result from this new approach are consistent with what people have have known since 1980, but we didn't make really too much progress. So we need to do more to break the status quo to further constrain this K naught and the high order coefficient of the symmetric matter. Okay, now let me move on to my next topic here, which is the neutron-proton effective mass splitting. So first, let me remind you the definition of the effective mass. The so-called K mass is due to the momentum dependence of the single nucleon potential, which reflects the fact that the nucleon-nucleon interaction has a finite range. Okay, the so-called E mass is related to the energy dependence of the single particle potential related to the finite time of nucleon-nucleon interaction. But once you introduce dispersion relationship, then the energy and momentum are related to this relationship. Then what we are talking about will be the so-called total effective mass, which can be calculated by either using the energy derivative with respect to energy or with respect to momentum. And the K mass and E mass are related to the total effective mass through this relationship. So when we talk about the neutron-proton effective mass splitting. We're going to talk about the neutron-proton total effective mass splitting in neutron-rich matter. Okay. Last time I discussed how the symmetry energy here can be related to the isoscalar and the isovector part of the single nucleon potential. Because the potentials are momentum dependent, we can define a neutron-proton effective mass splitting through the definitions I introduced to you. And this neutron-proton effective mass splitting is related to the momentum dependence of the isovector potential and the momentum dependence of the isoscalar potential. However, these two terms more or less cancel out. So the neutron-proton effective mass splitting reflect mainly the momentum dependence of this isovector potential. Now, if you use many-body theory to calculate the isoscalar and isovector potential as a function of momentum for a given density, like at 1/2 density, normal density, 1.5 times normal density, you see that it depends on the interaction you use. In this case, people use 11 popular convenient force to calculate this potential. You see that at high density, this prediction diverges, very broadly, although they can all very nicely describing many properties of finite nuclei. Okay, and I mentioned on the last slide that the momentum dependence of the isovector potential, isoscalar potential, affects the symmetry energy, and the momentum dependence of the isovector potential determines the neutron-proton effective mass splitting. So then, you can see that if you calculate the corresponding symmetry energy at a function of density, these different interactions give you very different prediction for the high density part of the symmetry energy. Okay, for the symmetry energy we discussed last time, there are some constraints below and around the normal density. For the isovector potential here, they do compare their calculation with this band here, which I'm going to discuss soon, is the optical potential obtained from analyzing nuclear scattering by Li Bao-An. He extracted this isovector potential at a function momentum. So you see that this constraint does help people to rule out some of the models. Okay, and I'm going to discuss that more. Okay, yeah, here comes. So Li Bao-An analyzed over 2,000 sites of nuclear scattering data. He then extracted the isovector potential and isoscalar potential and isovector potential as a function of nucleon energy. Okay, and also compared with previously known isoscalar potential and isovector potential. These few systematics are from earlier analysis of some limited set of data. Okay, so the new analysis track this isovector potential goes like this, isoscalar potential goes like this. So this potential has been used to constrain some of the model predictions. Now, okay, so I replotted here the isovector potential extracted by Li Bao-An in this range here. Okay, if you calculate using this potential to calculate the corresponding neutron-proton effective mass splitting, you find this one is about positive 0.4 plus minus 15 times the isospin asymmetry delta. Okay, because the neutron-proton effective mass splitting is related to the slope of symmetry energy and the magnitude of symmetry energy at normal density in such a relationship here. You can see that if you want the neutron-proton effective mass splitting to be positive, namely neutron effective mass is higher than proton effective mass, this requires the slope of symmetry energy at normal density to be less than 76 MeV. Okay. So we're going to discuss more on this. Also, before we go to the next slide, I want to point out that if you have an isovector potential like this going increase with energy, like the prediction from SLY4, okay, then the corresponding effective mass for neutrons will be less than protons. This is inconsistent with what one expected from studying the optical model analysis of nuclear and nucleus scattering. Okay. Well, earlier, Xu Chang actually used some earlier systematics for the symmetry potential as a function of energy from since 1976. People have tried to extract the symmetry potential from looking at, for instance, the single particle energy levels from pickup and stripping reactions, neutron-proton scattering, proton scattering on a sequence of isotopes or p-n charge exchange reactions. From combining the data from this different kind of analysis, actually in this book you can find the systematics. They are very limited in terms of energy, and also most of this analysis don't give you enough information about the error bars. So what Xu Chang did is just to take an average of these different systematics and see if we can get some useful information. Okay, that's the first attempt. From his analysis, because the symmetry energy has these two terms, if you know the symmetry potential at normal density, then you can calculate the magnitude of symmetry energy at normal density. You have kinetic part, potential part. It comes out about 31.3 MeV. Okay, with a relatively large error bar. This number is exactly almost the same as what we found from systematic studies of many observables. It's also consistent with some of you have extracted recently from analyzing a big side of the masses of nuclei. Okay, from the momentum dependence of the symmetry potential, he also extracted the neutron-proton effective mass splitting about 0.3 times asymmetric direction. The slope of the symmetry energy has these three terms in this particular model. It's about 50 to 53 MeV. It's also consistent with what we knew from other analysis. Now, how good is this number in comparison with some other analysis? Now here I put together this slide. Okay, it's a busy slide. First, let me point out that this range here between these two horizontal lines is the latest prediction by Tyler Whitehead using chiral effective field theory within their many-body perturbation approach. This is the uncertainty. This is the prediction done last year. Okay, I call it prediction. The analysis that Xu Chang did give us the neutron-proton effective mass splitting about 0.3 plus 0.15 with a large error bar. In 2013, Han Xiao and I analyzed the systematic of symmetry energy. We tracked the mean values here with even larger error bar. The analysis by Bob Charity in St. Louis, they used the dispersive optical model. They extracted the mean value here. Of course, in their analysis, they didn't try to infer the uncertainty because some limitations of their data set and model. The result from Li Xiaohua is here. So these are all from optical model analysis. Okay, they are all consistent with the latest prediction from chiral effective field theory. These few data points, okay, are from analyzing signal resonance and electrical dipole polarizability of light 208 by several people in China. Here, Zhang Zhen, Li Wen, Xu Jun, and his students. Okay, they are also more or less consistent with the chiral effective field theory calculation. Okay, now one interesting exception is a result from analyzing the neutron-proton ratio from Michigan State using the Beijing analysis within the improved quantum molecular dynamics transport model. This model gives you a neutron-proton effective mass as minus 0.05 plus minus 0.09. Okay, so this number is far below the chiral effective theory calculation. So there are some interesting things, some questions we need to further study. One thing I would like to point out is that all this these are from analyzing data on a single nucleus. They are at more or less at normal density, but this is from heavy ion collisions. During heavy ion collision, the density changes, the more things we need to do, I'm going to show you on the next slide. But before I go to the next slide here, I want to show you the results from the chiral effective field theory by Tyler and his collaborators. They predict that this neutron-proton effective mass splitting somehow increase a little bit and more or less, well, within this uncertain range. This is more or less like a constant and keep it going, okay? The chiral effective theory cannot be used to too high densities. And a normal density at the south here is consistent with what Li Bao-An expected, okay? So we need to learn more about how the neutron-proton effective mass splitting may change at a function of density. And this can only be done by using heavy ion reactions. So if we look, go back, look at the couple plots from a paper Li Wen and I wrote some years ago, looking at tin 132 and tin 124 reaction at 50 MeV. The maximum density here you can reach in this reaction is about 1.4 times normal density in a mid-central collision at 10 Fermi over C. If you look at the difference between the neutron effective mass and proton effective mass at low density, the neutron proton effect is still higher than proton, but the difference is very small. As you go to higher density, this range becomes larger. So it seems there's some indication that the neutron proton effective mass splitting will increase with increasing density. Okay, you can also calculate the distribution of this neutron proton effective mass splitting. Now, why it is important to study the neutron proton effective mass splitting? Because in a heavy ion reaction, the in-medium nucleon cross section is proportional to the nucleon effective masses, reduced effective mass. Okay, it's the square of the nucleon effective mass. Okay, so if neutron and proton have different effective masses, this will affect the cross section between neutron proton and how they are different from neutron or proton. This kind of cross sections are important for the stopping power, the dynamics of heavy ion reactions, in particular those nuclei with a lot of neutrons and protons. This cross section is also important for simulating the transmutation of nuclear waste. Okay, I know in China there are people trying to develop transport codes to see how effectively you can do the transmutation of nuclear waste. You need to use the neutron proton cross section in the neutron-rich environment, how that cross section is different from the free space. Okay, and that's determined by the neutron proton effective mass splitting. It has an important effect. So this is important for both reaction dynamics in free equation state and nuclear waste transmutation calculations. Okay, now let me come to my last topic about the neutron skins. And this is a hot topic, has been hot for many years. Well, okay, so here are first examples illustrating why neutron skin is a good place to study isospin physics. What's shown here is the neutron-proton ratio as a function of coordinate from the center of latitude 8 to the surface. Scaled, divided by the neutron-proton ratio of the latitude 8. Okay, so this is a scaled neutron-proton ratio as a function of distance from the center. This scaled density is more or less a constant 1 in the interior of latitude 8. Then on the surface, this ratio goes from 1 to 5. So this surface area is a good location place laboratory for us to test the isospin dependent physics. Okay, earlier studies by say Alex Brown and his collaborator have shown that the size of neutron skin is proportional to the slope error parameter. Okay, this error I discussed last time and also saw here, the air is proportional to the pressure of pure neutron matter at normal density, because there at normal density, the symmetric part of equatorial state is at its minimum. So the slope of this term is 0. So the pressure of pure neutron matter is determined by the air parameter. So you see, this is kind of empirical relationship. Okay, people have tried to argue why it is so by using this kind of argument, but I would like to point out that this kind of argument is useful for us to understand your calculation result, but it's also somewhat misleading. Okay, because the formation of neutron skin is really the result of competitions among, say, nuclear force, coolant force, surface tension, all those important things come in to determine your final neutron skin. It's not just the slope parameter L, and it's not determined by the slope L at the normal density, as Li Bao-An and Zhang Zhen have shown. It's determined by L at a lower density, around 2/3 of the normal density, not the L. Okay, so also I want to emphasize, when you go from 2/3 normal density to normal density, you need to do an extrapolation. That extrapolation is strongly model dependent. Okay, some of you may know there are people predicting that the size of neutron skin is correlated to the size of neutron star. Okay, based on some models, but be careful. That's very, very model dependent. Okay, well, why there are neutron skins? Okay, where are they coming from? Well, the quick answer is that, well, it's a result of minimizing the total energy of your system. Okay, I mentioned the competition among coolant force, surface tension, and nuclear force. Okay, if you just look at the equational state of asymmetric matter, you have this asymmetry energy term times delta squared. Okay, normally the symmetry energy will increase with density like this, at least, before you go above 2 times normal density, the symmetry energy more or less increase. Okay, so you see that at high density, the symmetry energy value is big. Then in order to minimize the total energy, you would like to reduce the idle spin asymmetry. While for the low density part, where the symmetry energy itself is small, this number is small, you would like to make the delta larger. So this will prefer, this so-called idle spin fractionation. You make the high density part, more neutron poor, make the delta small, with the low density part, more neutron rich. So this will naturally give you, a low density neutron rich system. Okay, just look at the uniform matter. Now, if you do a simulation, for instance, some years ago, we did by, showing some nucleons in a box, okay, in a region where the system is mechanically unstable, the so-called spinodal decomposition region, where the system is unstable. You start, expand according to the dynamics using transport equation, where the symmetry energy, will come in. You propagate the nucleons in phase space according to the Boltzmann transport equation. Okay, the symmetry energy will come in. You see that you start from here at t equals 0, and go to t equal to 50 Fermi ORC or 100 Fermi ORC. You see that this low density part, this is a density, this is idle spin asymmetry. This low density part becomes very neutron rich. You start from here, okay, delta equal 0.6, but this region is, directly above 0.8. So you naturally form a low density neutron rich system. The high density part here around, normal density becomes, very neutron poor. Okay, so this naturally leads to something like a, formation of a neutron cloud, okay, in space. Okay, now this kind of physics can be studied by using high-value reactions. For instance, if you use 2 different kind of symmetry energy, one increase linearly with density, like predicted by relativity mean field model. The other one increase first and then start decreasing. Okay, if you calculate the correlation between idle spin asymmetry and the density rho, you see that the low density part becomes very neutron rich. The high density part becomes relatively neutron poor, and the separation of this asymmetry depends strongly on the high density behavior of symmetry energy. So by looking at things like neutron-proton ratio of light particles, okay, immediate like pre-equilibrium particle, we can infer symmetry energy and also the neutron-proton effect mass splitting. So that's why people have measured the neutron-proton ratio, okay? And in this high density region, we can look at things like pi ratio, neutron-proton differential flow to probe the high density part of symmetry energy. And I know people like Zhigang has been leading a group in Lanzhou try to do things like this, and they have been doing some experiment already in Lanzhou and GSI. Okay, but anyhow, this also all illustrates the importance of symmetry energy in forming neutron clouds. Okay, surrounding a relatively neutron poor core. Okay, I mentioned that the slope of symmetry energy has these 5 terms. They are determined by the isoscalar effective mass, the momentum dependence of effective mass, the density dependence of the symmetry potential, the momentum dependence of symmetry potential, and all the higher order terms. And you have seen the calculation from Alex Brown, which shows that the neutron skin increase with the slope L. Then you may ask, which one of these different components are important for the neutron skin? Okay, to answer that question, Farouk did a calculation when he was doing his postdoc with me in Texas. We selected 2 interactions, 2 scrum interactions, SLY4, which has L parameter like 56 MeV, and NR-APR, which has slope of 60 MeV. They give more or less the same neutron skin because we purposely selected these 2 equatorial states, have more or less the same symmetric part of equatorial state, more or less the same symmetry energy at lower density but different high density behavior. Okay, and this tells you why the high density part of symmetry energy are different. Okay, but for neutron skin, okay, what's important is to see how which one of these different terms are important for neutron skin. To answer that question, we calculated the correlation function of neutron skin with the different components of the L parameter at a function of density. Okay, this is how you define correlation function for both LIDAR 208 and Keratin 48. Now, what you see is that at a function of density, this L4, which is the one that's determining the neutron-proton effect mass splitting, it doesn't change with density, and it's also very small compared to the contribution due to L3, which is this density dependence of the magnitude of symmetry potential. Okay, how it depends on the density. Okay, this is the only one that's changing. Okay, and it's dominating. So from here you can see that it is actually this term in the slope parameter L in this density region that's determining the size of neutron skin, while the neutron-proton effect mass splitting doesn't affect much the neutron skin. It's also important to remember, I told you that the SLR4 gives you a wrong neutron-proton effect mass splitting, okay, in comparison with what we extracted from analyzing optical model. But this here is say that this thing doesn't affect the prediction on the size of neutron skin. So you can still use the SLR4 to predict, calculate the size of neutron skin, okay? And don't worry about its its effect on the slope on the neutron skin at all, okay? Well, this is information from the correlation analysis. It's consistent with the traditional calculation done by people like Li Bao-An, okay? He calculated the size of neutron skin as a function of these different parameters, microscopic parameters used in the so-called modified Scrum Hartree-Fock calculation. You see that all these parameters doesn't affect much the size of neutron skin. The neutron skin only change, increasing with L. The other one doesn't affect much. And I showed you that it is the magnitude of symmetry in the L that's contributing, dominating this contribution. Well, let's look at some data, okay? Well, people in Lanzhou has evaluated the available data in the world for neutron skin, okay? They polluted, for instance, the size of neutron skin as a function of idle skin asymmetry for several isotope chains like calcium, okay? Calcium, neon, tin, Li-208. I want to point out that Li-208 had these three numbers here for three isotopes, which is much lower than the one from the recent P-Rex analysis, which gives a neutron skin of 0.28 plus minus this is 0.7, okay? And one zero missing. It's somewhere here, okay? When they analyzed they evaluated data and they did a calculation using the Sturm-Hardy-Fock, using SRL4, okay? The calculation agrees quite well with the data, okay? This is not a fit, okay? This is just a calculation. And I mentioned to you that this SRL4 gives you error around 46, but it gives you a wrong neutron-proton effect mass splitting. If you believe what I told you about the neutron-proton effect mass splitting from optical model analysis, okay? But I showed you the neutron-proton effect mass splitting has no effect on neutron skin, okay? So, you can see that this SRL4 gives you, calculating agrees quite well with the data, okay? Well, this is actually quite consistent with earlier calculations using the modified Sturm-Hardy-Fock by Li Bao-An. He calculated the neutron skin of tin isotopes, and you have the result from using R equal to 100, using 20, and he also did a K-square fit. The minimum is at around 55 MeV. So this number is consistent with what people extracted, the calculation done people in Lanzhou, okay? Now, this kind of calculation is the traditional forward modeling, okay? And you do a K-square calculation, okay? But when you have a model that has, say, 10 parameters, it's very hard to pin down a global minimum. You may have multiple minimum that are not too different from each other. So to overcome this difficulty, one can do the Beijing analysis. This was Xu Jun and Wenjie and I have done a couple of years ago. You look at the posterior distribution function of the isovector effect mass, L, and magnitude of symmetry energy and normal density. You see again, the effective mass or the magnitude of symmetry energy and normal density have no correlation. I mean, they are flight. Namely, the posterior one is the same as the prior. So the data on neutron skin doesn't, affect anything. Okay, it doesn't improve our knowledge about the effective mass or the magnitude of symmetry energy and normal density. It is the L parameter. And from the analysis of the tin data, one can see that the peak of the posterior probability distribution function peaks around 60 MeV, which is consistent with the prediction from chiral effective field theory, also consistent with what we learned from analyzing neutron stars. In my next talk, I'm going to talk about how we track the symmetry energy from neutron stars. Is this one here. So the neutron star chiral effective field theory analysis of tin isotope all give you L parameter around 60 MeV. Okay, and these are consistent with analysis done by people in Lanzhou and also by Li Bao-An. Okay, now then you may ask a question: if you trust the chiral effective field theory, the data from tin isotope, okay, can you make a prediction? Okay, in the same model for Li-208 and calcium-48. So what we did, you can imagine, make up some, some data, okay, for Li-208, put in your Bayesian analysis, and then see, what kind of data you have to put in, fake data you have to put in, what kind of error bar you have to put in order to get a posterior distribution for the error parameter to be consistent with what we know about the L parameter from earlier analysis. The conclusion is that, well, the light 208 has to have a neutron skin around 0.18 Fermi. The uncertainty has to be very small, like less than 0.02 Fermi, in order to have the PDF of L consistent with what we knew from analyzing thin isotope and neutron stars. For calcium 48, we try to imagine, the size of neutron skin. We use as guidance the prediction from couple class model, which predict around 0.12. The self-consistent Green's function predict quite a large neutron skin, like 0.25. We found that the neutron skin of calcium 48 has to be somewhere in between around 0.15. Okay, and this is also not a real precise prediction. It's around this region. Okay, it has to be relatively small. Well, so let me use let me speed up just maybe 5 more minutes to briefly discuss what people have found from the P-Rex experiments, where you use electron scattering on light 208. Electron can interact electromagnetically by exchanging a 40 photon with a nucleus, or Z boson due to the weak interaction. The total cross-section is a square of the matrix element squared. If you neglect the square of the weak interaction part, what's important will be the interference term between electromagnetic interaction and weak interaction. If you if you take the difference of the cross-section induced by the longitudinally polarized electrons, take the difference between right-handed and left-handed helicity, then you cancel out the contribution from electromagnetic force. You're left with this term. And also, if you divide it with the sum of this cross-section, you find that this strength of parity violating scattering is proportional to the weak charge form factor over the electromagnetic charge form factor. So by measuring this quantity here, which is very small, like 1 out of 1,000,000, you can then infer the weak form factor, since the charge form factor is well known. Okay, but there is a kind of difficulty here, not only because difficulty measures such a small thing, but also because the current experiment can only infer the weak form factor at a single Q value. In principle, you need to measure the form factor at a series of Q value. Then you do an inverse Fourier expansion to infer the nucleon charge, the weak charge distribution, which is essentially the neutron density distribution. But at the moment, there is only one data point. So what people do is to assume, a distribution like this, like a Gaussian distribution with the form factor. So the data analysis is through this procedure. You measure the parity violating strengths, and then you do, make a Coulomb correction, assume this and this. Finally, you end up with neutron skin. The claim has been, okay, the result is largely model independent. And how large it is, really up to you to determine, okay? Personally, okay, I might be wrong. If I look at, the so-called the skin of form factor is a difference between the charge form factor and the weak form factor as a function of momentum transfer Q, okay? Well, different model predictions do, more or less the same in this region. And here is very depends on the size of neutron skin, okay? So the hope is that by measuring the form factor at a single point, like P-Rex or C-Rex, you can then determine the neutron skin, okay? But if you're critical as myself, okay, sorry, I might be offending some of you, okay? This looks like you assume all elephants have the same shape. Big elephant, small elephant have the same shape. If you know the size of, say, the nose of elephants, okay, then your model tells you the size of the whole elephant, okay? but that's the best, probably the best you can do at the moment. You only have 1 point, okay? That's what people done at the P-Rex or C-Rex, okay? So P-Rex measured the parity violating asymmetry. This is the data. And this is the calculation from relative mean field model using different forces. Then this gives you the weak radius, the corresponding neutron skin, okay, around 0.3. This neutron skin, according to their calculation, gives you L parameter around 106 MeV, and this distribution, this favors, okay, this favors the prediction of chiral effective field theory. All these microscopic of initial calculations are disfavored by this data. Of course, the systematic, I have been showing you around 60 MeV. It's also disfavored because 60 MeV is about the average value here. Okay, this is the P-Rex. The recent C-Rex data for the neutron skin give you C-Rex preliminary data is about 0.1. Okay, so the interaction that predict neutron skin consistent with P-Rex 2 for light 208, or none of this calculation can give you a neutron skin for calcium 48 in the range around 0.1. So there is a complete disagreement between the P-Rex 2 and C-Rex preliminary result. Okay. Also, the P-Rex 2 results, here, the radius for predicted radius for neutron star of 1.4 solar mass is above 13 kilometer, which has a large disagreement with the nicer observation. Also, the predicted tidal polar radiability is much larger than the upper limit of LIGO. I know some of you have been making efforts to try to reconcile this one, but if you consider a new result from the C-Rex, which prefers the radius much lower than 12 kilometers, there's no way to, well, I shouldn't say, I'm sorry, I shouldn't say no way. Okay, there is definitely a tension here. Okay, so that's the status of neutron skin from parity violating electron experiment. Now, with this information, we may need to go back to our traditional hadronic approach. Because I'm running out of time, let me just quickly say several groups, in particular, several groups in China have looked at how the neutron skin may affect observables in relativistic heavy ion collisions, such as pi ratio, pi minus pi plus ratio, or several other observables. Okay, at high energy, this is a prediction by a group at Huzhou under the leadership of Fu Qiang. Okay, using several high energy models. People in Shanghai also look at how the neutron skin affect protector fragmentation. People in Germany and France look at again how the neutron skin affect pi minus pi plus. So all this showed some indication that the neutron skin affect significantly heavy ion reaction observables. But so far, all these analyses have considered basically, either this like a byproduct of studying something else, or just look at this as an uncertainty of some other observables. None of this have been used to actually extract a number for the size of neutron skin. So I hope, with current situation from J-Lab using parity violating scattering experiments, we may want to look further about it, what we can do with this is traditional hadronic approach. Okay, so just a point to make. Now let me come to my summary. I have 3 slides. The first slide I saw you last time. This is a slide I prepared for a summary talk I did at the Nuclear Symmetry Energy Workshop at the Michigan State in 2013. This showed you that the slope parameter L from 29 analysis available at the time give you L around 59 MeV, plus minus 16. I saw this same slide at these 2 workshops, one at JLab they invited us, a small group of 20 people, to discuss the C-Rex proposal and revise the P-Rex2 proposal. I saw this one there, and I also saw this one in Germany when they were planning a new experiment in Germany. Several people don't like it, okay? Because the proposal is to say that the P-Rex experiment, C-Rex, will give you the most precise determination of error with model independence, without any model. But this, reads a question. I want to read it here, okay? I don't know the answer. So is there a, democratic principle in physics, okay? Well, I make that point because now, if we go beyond this 29 analysis, look at it, totally, there are about 80 analyses, including the recent, like 24 analysis of neutron stars. They all give you the L parameter, okay? Around 58 MeV or so, okay? Also, I have this, again, the slide about the neutron proton effect mass splitting, because the effect mass splitting is related, give you a constraint limit on the L parameter, okay? And there are also some questions here. So, okay, I just want to stop here and thank you for your attention. I would be very happy to discuss any questions you may have. Thank you very much for your attention.
我们非常感谢这个李博，非常感谢李博安教授的这个报告。下面看大家有问题。真信。
喂，李老师。
嗨，英迅你好。
哎，李老师，那个李老师报告每次都学的不少东西啊，非常。那个我有个问题啊，就是那个 Prix2 那个，它那个分析就是肉 n 或者肉 p 那个实验上它那种分布，它是不是这个？我印象中好像文献看是伍兹萨克森的分布，是不是这种分布对它那个实验结果也有影响？
可以，你能不能重复一下你问题？我没有完全听懂你的问题。
啊，就是说，当时我看就是那个 Prix2 李老师放的那个片子里面，关于 Prix2 那个结果，他们那个实验。
现在我把那个放上，你能看见吗？
不是这一篇，不是往前有一个他那个 form factor。
对，这个吗？
还有一个公式，在前面上一页。
这个。
对，就你看这个 form factor，它这儿那个 ρ PR 跟 ρ NR， 我印象中看他那个文献是，他那个 ρ PR ρ NR 是不是用的那种伍兹萨克森形式的那个密度分布？
你说就是这个就是他
对他实验上分析的时候是不是用的这种？是不是这种会导致他的这个结果不是特别好？就是那个出来那个 Prix2 那个中子皮那么大。
OK， 这个我要 double check， 我不是完全说，他是就是放到这个里边以后，他给一个 ρ n， 它确实一个 parameterize 一个，我现在好像就是 Woods section 那个 form， 然后呢他调那个两个参数。OK， 最后给出一个就是有两个 term， 有一个就是所谓的 weak charge radius square， 还有一个false power term。然后你看那个就是这个文章里对，你看他的，我看要仔细看他的。
对，我看他那个文章，我印象中他就是伍兹萨克森那个形式。
对，我感觉也是这样，就是
如果这样的话，那这个就是说。那实际上那个铅可能出来那个中子，比如说用 Symmetry Fogg 算的话，肯定跟那个是有些差异的嘛。就是这种会不会有？
对，是这样。你那个你可以看他那个就是这篇文章 review 文章里面，他们也那里边给那个公式给出，就把那个展开以后，用伍兹萨克森式放进以后，然后做展开，把那个 weak form factor 能写成一个 Q square 的函数，然后那个系数呢就和那个 weak charge 的 radius square 和radius false power 连起来了。在这边那个 review 文章里面，它具体 data analysis 你要看它那个文，但是呢，它 PRL 文章没有多少仔细的 information， 就主要是这个图在内，它的 PRL。
对，我就感觉它密度分布用的不对的话，用的话不合适，跟咱们比如说抽其他模型抽中子皮那个 不一致的话，可能这个是不是对它这个结果
也有可能？
你
应该 OK， 你要 look into that， 因为他们 claim 是这个，他们结果是 model independent。
哦 ，OK， 好，谢谢李老师。
OK， 你好。
这个他们都做过 check 的音讯
啊。
就用这个 Horowitz 他们用相当平常，还用这个 suction 是这个 model dependence 应该是很小，
是吧？
对，他们做过 careful 的这个 test。
对，就是比如说你上次陈老师说的这个，如果它有 cluster 这种东西，它的密度分布是吧？是不是也有变化
？Right， 如果有 cluster 那就是 new physics 了，
对吧
？OK， 那个对，那就要到那个 Stephen Keeple predict 在那 light way 的 surface 上有这个 alpha cluster， 而且他那个 science 文章里面他就说这个在 Riken 发现了 Riken 和那个 RCMP 就是发现了这个 evidence。
对，如果有 cluster 就非常有意思的一个。
对。
只是表面上，对，最底线。
好，我看还有谁有问题吗？
李老师，我那个请教一个问题，谢谢您这个报告辛苦了。就是我在那个 textbook 上看那个 binding energy 结合能，它那个对称能是一个加号，是一个减号。然后在咱们这个状态方程和物质状态方程里面，对称能是一个加号，为什么这两个符号是相反的？
这个就是，这个就是一个是你怎么比你的 binding energy 和那个就相当于一个 bind system 和一个就是把这都散开以后，这个两个 energy 就像我们在算那个 mass formula 都是这样做的。
这两个不矛盾吗？
不矛盾。不矛盾。
好的，还有一个问题就是这个咱们这个斜率大写的这个 L， 它一定是我看它有的时候也是会小于0是吗？什么情况它是大于0？什么情况小于0？为什么它会大于0或者小于0
？OK， 在 normal density 的时候不会小于0，都是 positive。normal density 就是 normal density 附近都是 increase with density。小于0的是只是在那个 high density 那个 local slope of symmetry energy 在非常 high density 的时候，按照有些 model prediction， 有些 Sturm-Hardy-Fock 或者是像那个 variation many-body theory， 它 predict 在 high density 的 symmetry energy 可能变成 decrease with increasing density， 但这个事情都是在3倍的 normal density 之上有可能发生，在 normal density 不会发生，肯定是 positive。
它为什么会发生呢？就是在那个高密度的时候，为什么会
OK， 在OK， 这是一个很有趣的问题。这个在 high density 的时候，按照有些 calculation， 我就说那个 various many-body theory， 那个比如说那个阿刚的 group， 他们argument 是这个就 go back to tensor force，OK， 因为 symmetry energy 是 energy difference between 这个 pure neutron matter 和 symmetric matter。在 symmetric matter 里边有这个 neutron proton interaction， 主要是 neutron proton interaction 嘛。在 neutron proton interaction 有一个 tensor force， 那个 tensor force 它那个随着 density 增高，那个 contribution to the symmetry energy 会增大。所以呢，在 density 高到一定程度之后呢，这个 tensor force contribution 使得那个 energy per nucleon in symmetric matter 会比这个 pure neutron matter 还要高，所以这两个 difference 变成 negative。因为 symmetry energy 是 defined as energy in pure neutron matter 减去 energy in symmetric matter。如果在 high density 里边，你那个 energy in symmetric matter 增加的比这个 pure neutron matter 还要快，那个 symmetry energy 会变成 decrease with increasing density。这主要是 tensor force 的影响。这个是就是有些 calculation 是这样 predict。
但是这个只是理论的预言，并没有证明它会变
没有就是这个预言，就是说当然就是说我们看到一些，比如你问肖志刚，我们多少年之前 analyze 那个肖志刚一起 analyze 4P data 就 GSI 的 data， 发现那个 time ratio indicate 这 symmetry energy 可能在 high density 会向下降。OK， 这个东西会影响 neutron star 的很多 dynamics。现在的就是说没有一个 complete 就是 consensus， 没有一个 conclusion。现在的 neutron star 给你 constraint 是给一个 range， 那个 range 不 exclude 这个 decreasing symmetry energy。所以在 high density 的时候，这个 symmetry energy 可能会随着 density 会降下来。这个就是那个 Monkey Row 和这个国内的一些人在杭州的有一个教授的名字和你很相像马教授，这现在在杭州，原来吉林大学的他们
马永亮，
对马永亮，他们 predict symmetry energy 在 high density 就是3倍之上，可能还有一些 structure， 有一些little tip and 可能 increase。OK， 所以这个 high density behavioral symmetry energy is very uncertain。OK， 那个东西会对 neutron star 有影响，对 high field colliding 也会有影响，所以这个也是一个 motivation for doing high energy high field colliding。
是的，是的，我理解您的意思了，谢谢。
我看还有没有问题？
杨老师北大杨老师有什么问题说？
那个李老师好，我是杨在宏
你好，
现在北大。那你好，就是说首先那个就是刚你们提到那个 Science 的文章，就是我在日本的时候跟那个合作组我们一起做的，就那个表面就是发现那个阿尔法那个工作。
对。
所以我们对就是你刚刚你说的这些事儿就是我们都挺感兴趣，也是一直的非常关注，就是因为我们那个工作实际上相当于是一个怎么说一个起步就是我们发现了一个现象。那未来嘛，我们还有一系列的工作是说把这些事儿呢想做得更细一些，也希望以后我们有更多的机会可以讨论合作
对，很好啊。如果你们能够就是除了 light to way 的，还能做一些其他的，然后能把一些更多的 information 能够提出来，这样的话就是对我们做 structure 或做 reaction 都会有影响，就是这个 signature 很重要。这个如果真是那个在 neutron 在 light to way surface 上有这个 alpha cluster， 这个结果确实很 exciting， 有很大 effect。
我们那个有一系列的那种 PPR 的实验，就是在 RCND 还有那个锂已经在计划当中。
OK， 那非常好。祝你们很快有更多的成果出来。
谢谢老师。我想问个问题就是那种比较 general 的一个问题就说像现在像你们做这种理论计算的时候一般就基于某种这种相互作用像你这个图上这些，比如说那个 lead to 8他们用的各种相互作用，像这些有些相互作用一般都是根据这种有限核的一些性质理合得到的，对吧？一般情况下，
它是这样，就是一般情况，比如说这个 TAMUCB这是法入，他在我这儿做 postdoc 的时候。OK， 它这个就是 modify 它的 original 这个 FSU gold interaction。OK， 然后呢，用那个 interaction 当时是想 reproduce 这个 P-Rex1 的 date，large neutron skin。但是呢 ，OK， 你看它有 big apple， 这 big apple 呢是它的 interaction 想调了以后呢，想 reproduce 那个就是那个 2.5 solar mass neutron star， 就是什么说它。首先，那个 interaction 要 reproduce the saturation property of nuclear matter，OK， 这是一个 constraint。然后呢，再用那个 model 来算一些这个有限核的一些性质，包括一些那个 energy level 的 splitting， 那里边有很多 parameter， 包括这个就是这个主要现在 isovector 那个 coefficient，isovector interaction coefficient 是 unknown， 所以确实要 reproduce 一些 finite nuclei 的 parameters。OK， 然后用来再做其他的 calculation， 这个国内很多人都做过这个事情，都做了很多。
就像这种，比如说现在你们去算不同的这个密度区的这种性质的时候，这个相互作用它会做一些什么调整，以考虑这种密度依赖这种行为吗
？Suppose 现在是大家就是应该是这个 parameter 应该在 saturation point 所定下来了，然后呢也 feed 一些 finite nuclei parameter， 然后用来做 prediction at high density。那个就是 suppose density dependence 不会变。
明白了。
那个就是那个 coefficient 不会变了。但是就是说，然后用那个你来再算那个 Neutron-star property， 你想用 Neutron-star property 来定你的 prediction。
好，
基本上是这个思路。
另外一个我刚忘了说了，就是我们那个工作不是说发现这个正好表面，比如10208，它可能有个 alpha cluster， 但实际上它的效应跟那个Prix2 那个是反的，就是说我们认为有 cluster 之后，它会让的中子体反而更小，但是呢Prix2 反而给出来的中子体比大家预想的更大。所以从我们实验的角度，看到这种推行了，当然很高兴，对吧？但说明有很多东西我们还要接着去做，大家接下来几十年会很活跃。
OK， 这样很好。就是我当然我make一些 comment 可能比较 negative， 但我是希望见到这些，就是不能解释的事情。OK， 很多这个就是contradiction， 所以我今天 talk 主要 focus on the question， 哪些地方有些问题，大家的就是 historical problem 到现在还不能解决。OK， 有现在这些新的 experiment 能够给大家一些就是说一些这个 hot points， 这一些 question， 主要我们要找 question。我们是光做 CRI 的开做 prediction 没用，要有 experimental 的这 puzzle， 我们需要找更多的 puzzle， 更多的experimental findings。OK，
对，
所以你的结果和他们不一样，这个东西对我们来说很 exciting。
对，好了，好，谢谢李老师。
OK， 谢谢你。
还有别的问题吗？李老师，我问一个问题，就现在那个状态方程的约束啊，就是不是实验数据也已经有了很多嘛？但是你假如想要进一步更缩小这个约束范围的话，你觉得在实验数据哪些实验观测量，或者是需要精度更高，或者是要增加哪些实验观测量才能够更有效的约束这个状态方程的一些参数啊？
哇，这个问题确实是不好回答。就是我们也一直做这个 prediction， 想找这个 predict 就是 observables， that are sensitive to symmetry energy at different densities。OK，so 比如 high field collision， 我们说比如看 pi minor pi plus ratio， 这个 uncertainty 应该就是比如小于这个 10% 或者多少。因为我现在 predict effect 也就是比如 10-20%， 所以那边有很多 model dependence。我的建议是这样，就是说。我们需要这个，刚才就有点和那个杨大红刚才讨论那个联系起来，就是说我们要有真的像做天体那样有这个所谓的就是这个 multi messengers。OK， 你光一两个 observer 不够，要很多 observer， 尤其比如像我提到说你那个，比如说 neutron skin， 只是就是 sensitive to 这个 magnitude or density dependent on symmetry energy。OK， 不 sensitive to neutron proton effect mass split。但 neutron proton effect splitting 又就 determine 这个 optical potential， 所以我们需要有这个，比如说你 optical potential 要有 ，OK， 在不同的 energy 就是 energy 更 neutron-rich，OK，optical potential， 然后你再 measure 比如 pi minor pi plus ratio， the neutron proton ratio，you know at different energy of flow or something，you know we need a kind of really you know full pi detectors measuring simultaneously。You know, multiple observables, OK， 然后用那个 multiple observable， 你才能 determine simultaneously multiple parameters, OK. So that's what astrophysics are doing. They are really doing this, you know, multi-messenger astronomy. We need to do this multi-messenger nuclear physics, OK. You know, if you just fit one parameter, I mean, you reproduce, you know, one data point. For instance, like this one, you just have one point, and then you try neutron skin, OK.Probably that's not enough. If you know combine this data with the data from Yang Daihong and his collaborators on you know alpha clustering emission, you know maybe also combine with pi minor pi plus ratio from high energy. You know you have to do a comprehensive analysis. That's my thinking.
好，谢谢。还有没有别的问题？ 好，要是大家没问题的话，那我们最后再次感谢李保安教授的报告。
好，谢谢啊。OK，再见。